All right, now I would like to talk about gravitational potential energy, because the force here is a conservative force. It comes from the derivative of a potential, and so we will have a potential energy associated with it. And so let's see here, to simplify, just to remind you that the change in potential energy is equal to negative the work done by the force. And the work done by the force is the integral, so it's minus the work done by the force, from x initial to some x final of f dot dr, f dot dr. Let me put here r initial to some, so from r initial to some r final, right? Some r final. So r initial to some r final. And so let's see what happens. So let's say you have a mass capital or mass 1 here, and here is mass 2 here, and let's orient them along the x-axis to make everything easier. And so this is the initial position, x initial, and a little bit later, let's say the planet has moved here, so how much work was done by this force? So let's say a little bit later, this planet is here. Let me draw it in black. So a little bit later, it's here at some x final. This is M2. It has moved from here to here. And so what would be the work done? Well, you see here, this planet, the force on 2 due to 1 is this way, and the motion is this way, so there is a 180-degree angle between them. So the dot product just will have the magnitude of F times the magnitude, since they're oriented along the x direction, let me just do it specifically for our problem, would be negative the integral from r initial to the r final, x initial is equal to r initial, and x final is r final. And then so it will be the magnitude of the force F times dx times the cosine of the angle between them, which is 180. So I would have a minus sign. So cosine of 180 is negative 1. So this minus sign will go away. So there will be, let me just put it here, cosine of 180 degrees, just to emphasize it. And so cosine of 180 times this negative sign becomes just positive. So the minus sign goes away. So I have r initial to r final. Now, what is the force? The force between them is capital G times capital M times little m divided by the separation between them squared, that's x squared, and then dx. The fact that the force points left, I took care of it already with this cosine of 180. So now you have capital G, capital M, little m. What's the integral of 1 over x squared? It would be negative 1 over x. You can take the derivative and verify that it gives you the derivative. It will give you 1 over x squared. Evaluated between r initial to r final, and this is delta u. It's delta u. It's u at r final minus u at r initial. U at r final minus u at r initial. And then here u at r final minus u at r initial. At r initial. And let's evaluate this. So this becomes the following. It becomes negative G capital M little m over, this should say r final. At r final, and then minus minus becomes plus, so plus G capital M little m over r initial. Like this. So this is the difference between them. And now let's say my planet goes from, not just from x initial to x final, let's say it goes to infinity. I want to know what would the potential difference between this and infinity. So if I take the limit as r final goes to infinity, this becomes the potential at infinity minus the potential at r initial will equal to What's the limit as r goes to infinity of this? Well, when r goes to infinity, this becomes 0. So it just, take the limit as r goes to infinity. This is r initial, that's a constant, so whatever it was. So this just reduces to capital G m over r initial. Now, whenever we talked about potential energies, we chose a reference point where that potential energy is equal to 0. And so our choice, when we were near the surface of the Earth, we chose the surface of the Earth to be the 0. But here you have planets and you have different things moving, different surfaces, different radii. So where should we choose the 0 to be? The best point to choose the 0 is, it will be at infinity. We say when the planet has moved infinitely far away, let's say two planets are infinitely far away from each other, or two objects infinitely far away from each other, their potential energy associated by their with their location relative to each other will be 0. So we choose u at infinity. It's a choice. We chose that to be the 0. Therefore what? Therefore, negative u at any r initial, I'll just drop the initial, at any r, will equal to g capital M little m r, and so u of r will equal to capital G capital M little m over r with a minus sign. That's the potential energy. Okay? That's the potential energy associated with this. So if I ask you, the reference point would be infinity, so what's the potential energy of this planet with this one, of these two masses associated, the gravitational potential energy? It would just be the product of the two masses divided by the separation between them. And then there is a minus sign. The minus sign, it's actually nice. It tells you that this is trapped. It has negative potential energy. In order to free it, you have to give it enough kinetic energy to overcome that potential energy and escape the gravitational pull, right? And so we have this. So let us do an example here. Let me see how much time I have. Okay, I have plenty of time. So let's keep this equation in mind. So the problem we have is, it says, suppose the Earth stops moving suddenly, right? It stops moving. And if it stops moving, let me just draw here. Here's the sun. Here is Earth. Normally it would go like this, because it has some tangential speed. Every time it moves here, it has already moved here due to that tangential speed. And when it moves here, it has already moved here. And when it moves here, it has already moved here due to that tangential speed. So it never hits the sun. It's always falling towards it, but it has that tangential speed. So imagine it stops moving for a moment. Imagine it just stops moving. Not stop moving, the tangential speed is 0. So it comes to here, right? So what happens? Well, if this initial speed is 0 and the force is this way, it will accelerate toward the sun. And so the question is, what would be the speed of Earth when it hits the sun? So we have it here at r initial. And then when they come close to each other, here's the sun. I will draw them a little bit bigger so you can see it. And then, so here is r final when they hit r final. R final would be the radius of the Earth times plus the radius of the sun. Would be the radius of the Earth plus the radius of the sun. And they're given to us. We have that number. Okay? So let's see. The total mechanical energy at the beginning will be, you see here there are no frictional forces or anything, so it's conserved. The mechanical energy before the collision and mechanical energy right up to the collision will be conserved. So the mechanical energy here will be the kinetic energy initially plus the potential energy initially. I'm talking about Earth here. If it stopped moving at that point, V initial will be 0. So the kinetic energy will be 0. Just be 0. And this is the potential energy. And the potential energy will be, remember, it's negative the mass of the Earth, sun times the mass of the Earth, and then the gravitational constant divided by the distance between them squared, r squared. I'm sorry, not r squared, just r. And I'm going to look that number for you. And the distance between the Earth and the sun is 1.5 times 10 to the 11th. So let's write it here. R initial is when they are far away. 1.5 times 10 to the 11th meters. And R final, which is the radius of Earth plus the radius of the sun, Earth plus the radius of the sun, that's R final, will equal to how much? Let me just write it down. 7.02 times 10 to the 8th. 7.02 times 10 to the 8th. 8th meters. So this is the potential energy at the end. Now, the energy at the beginning, the energy right before they hit, I call it E final, would be the kinetic energy there plus the potential energy there. Oh, okay. And so the question is, with what speed will Earth collide with the sun? How fast will it be moving when it hits the sun? Assuming it started at 1.5 times 10 to the 11th, and then it moves to 7.02 times 10 to the 8th. Okay. Well, let's see. The kinetic energy there will be 1/2 m, the mass of Earth, v final squared, plus the potential energy there, but the potential energy over there will be negative g capital M little m divided by r final squared. R final, not squared. I keep squaring it. That's the force. The potential energy does not have a squared over there. So let me a plus and a minus. Just put a minus here. No non-conservative forces involved. Yes, after they collide, there will be non-conservative forces involved and so on. But this is up to the collision. Way before the collision and then up to the collision. With what speed will it impact? So these two will be equal to each other. So the energy at the beginning will equal to the energy at the end. And so we get negative capital G capital M little m over r is equal to 1/2 m v final squared minus capital G capital M little m divided by r final. And you notice the mass of Earth simply goes away. So I'm going to move this here, move this one here. So I will get negative G capital M over R. When you move this one here, it becomes positive, so it becomes capital G capital M divided by R final equals to 1/2 of V final squared. I hope you see that this minus this will be a positive quantity because I have V squared, it better be positive. Because R final is less than R initial, so here you're dividing over a smaller number and here you're dividing over a larger number. So it will be, this number will be larger than this, so it's fine. So I get V, or V squared would equal to 2. I would factor the GM, and then here I have 1 over R final minus 1 over R initial, like so. And I would take the square root of both sides, and then we can just plug in the numbers. So you will put 2 times capital G is 6.67 times 10 to the minus 11. The mass of the sun is huge. I don't remember it. Like 10 to the 30th or something like that. I don't even have the I don't have the number at the moment. So let me just write it down. It would be 6.13 times 10 to the 5th. I can find the mass of the sun, but I think it's unnecessary. You can plug in the numbers yourself. Our final will be 702 times 10 to the 7.02 times 10 to the 8th, and our initial is 1.5 times 10 to the 11th. So I will just write down the answer. I have it as 6.13 times 10 to the 5th. 6.13 times 10 to the 5th meters per second. That's how they would, that's the speed with which it impacts. So this is V. Let me write it here. Let me just copy it. I get V is equal to 2G capital M 1 over R final minus 1 over R initial, the square root. Square root. And so we got this answer by using conservation of energy, which made life much, much, much easier. We can do it using Newton's, just directly by using Newton's law, the second law, F equal to ma. The book here says, it's worth noting that we do not have the mathematical tools to solve this problem using Newton's second law because the acceleration is not constant. I argue that we do have the mathematical tools to do it, and in fact, the author himself did it back in chapter 2. Let me show you what I mean. We know that the net force on an object will equal to the mass of that object times the acceleration. The net force on our object is capital G, capital M, little m divided by the distance squared. And the distance squared it's along the x-axis, so x squared. And here, little m times the acceleration, and the acceleration is dv dt. And the mass cancels. So I get capital G, capital M over x squared is dv dt, but by the chain rule you can put dv dx, dx dt when we derive the equations of kinematics, one of them. It looked like this. And then dv dt is, dx dt is the velocity, and so you will have here g capital M over x squared equals to dv dx times the velocity. So this is v, it's the velocity. I'm going to separate this, multiply both sides by dx, so I get v dv will equal to g capital M over x squared dx. And we're going to integrate both sides. And v goes from 0 to some final velocity, that's what I'm trying to find, and x goes from r initial to r final, r initial to r final. And let's see what this integration gives us. You integrate v dv, you get 1/2 of v squared. So you have 1/2 of v squared evaluated between 0 and v final. And here, when you integrate 1 over x squared, you get negative 1 over x. So this is negative g capital M over x evaluated between r initial to r final. I can just put r initial on top, r final on the bottom, and then take the minus sign away. So I'll put r final here. Just switch the limits and switch the sign here. R initial. So this becomes just 1/2 of v final squared equals to capital G capital M divided by r initial minus capital G capital M divided by r final. Multiply both sides by 2 and factor the gm, so you get v final squared will equal to 2 gm times 1 over r initial minus 1 over r final, and then take the square root of both sides, and we get exactly the same result, but it was easier using the conservation of energy, I argue, but we do have the tools to do it. I think all of you are able to do this. But again, conservation of energy, whenever you can use it, it's much easier. It makes life easier. Okay, so the next problem I want to do is called the escape velocity. So here is the pan. I throw the pan straight up, it comes down because it's bounded to the earth. It has a negative gravitational potential energy if you look at the big picture. So it goes up and then the earth pulls it down. If I give it higher speed, it will go higher, but it will come down. But if you give it high enough speed, it will go away and never come back to the earth. And the question is, what is that escape speed? How fast should you push it? We will rely on conservation of energy again. So let's see. So I would like it to leave and never come back. So it basically goes to infinity. So here is, now we're talking about Earth. Here's Earth. And then here is my little mass here. I'm going to give it some speed here, v initial. And I would like it to go away, to just go away. So first, here is our Earth, the radius of the Earth, and I would like it to go to infinity. So first, what is the initial kinetic, the initial total energy? It will be the kinetic energy at the beginning plus the potential energy at the beginning. Kinetic energy will be, of our little mass, it will be 1/2 mv initial squared. And then the potential energy is negative g capital M little m over r, right? By definition of potential energy, gravitational potential energy. That's that. The reference point, it will be 0 at infinity. And then the total energy at the end, I want to give it just enough speed to go to infinity and never come back. Ideally, I want it to go to infinity. When it reaches infinity, if I gave it just the minimum speed, the speed at infinity will be 0. So this will be the kinetic energy at infinity plus the potential energy at infinity. I would like the kinetic energy to be 0 and the potential energy to also be 0. By definition, potential energy, the reference point is at infinity, so this is 0. Kinetic at the total energy at the beginning equals to the total energy at the end. We get 1/2 little m v initial squared minus g capital M little m over r. Want it to be 0, and therefore 1/2 v initial squared equals to g capital M over r. I canceled this one. You divide both sides by m. And solve for v. So you get v initial, the escape speed, would be 2 capital G capital M divided by r, the square root. And r initial was, it started at the surface of the Earth, so the distance between the mass to the center of the Earth is the r of the Earth. So you get 2 times g, which is 6.67 times 10 to the minus 11. I happen to know the mass of the Earth, 5.98 times 10 to the 24 divided by the radius of the Earth, which is 6.38 times 10 to the 6th power. You take the square root, and that will give you the escape speed, escape velocity. So we get 2 times 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24th power, and then divided by 6.38 times 10 to the 6th power. So I get a number here, and then have to square root it, and I get about 11,182. Let's see, 11,182 meters per second, approximately, which is about 25,000 miles per hour. Miles per hour. Approximately 25,000 miles per hour. And so that is that. Sounds good. I just want to show you one more thing about this gravitational potential energy near the surface of the Earth. And then we'll do a couple more examples, I think, and the chapter will end. It's not as long as the previous chapter, angular momentum and rotational motion. That was a long chapter. This one is not that long. So let me erase this. So let's say near the surface of the Earth. Actually, I have to show you something about approximating things. There's something in Calc 2, you probably remember Taylor expansion, or the binomial expansion. If you have 1 plus some x, and x is to the nth power, if x is much less than 1, if x is much less than 1, let's say it's 0.001 or something, then this is approximately 1 plus n times x. 1 plus n times x. For example, let's say 1 plus, let's say 0.1 to the cubic power, right? 0.1 is not much less than 1, but it's less than 1. So this would be approximately, the approximation says it's about 1 plus, capital N here is 3, and the times 0.1. The x is the 1. So x is 1. So 1, x, and n is 3. So this says I should get 1.3, right? 1.3. Let me use my calculator here and show you. So 1 plus 0.1, let's get the exact answer. And then I want to cube it. So it says the exact answer is 1.331. You might say, well, this is not very good. But for example, let's say if this were 1.01, if it were 1 plus 0.01, it would be a much better approximation. So it would be 1 plus 3 times, the approximation would be this, which is 1 plus 0.03, which is then 1.03. But the exact will be this, 1.01, 1 plus 0.01 to the cubic power, to the third power, gives me 1.03, and then 0301. So that's much better. And you can imagine if this is 0.001, it will be even better. So here's the approximation that we're going to use. We're going to say, all right, near the surface of the Earth, we said if we chose our potential energy to be 0 at infinity, then the potential energy is U equal to negative G capital M little m divided by R, right? By R. So let's say here's our object, and we're near the surface of the Earth. So this is Y here, the height is Y. And so R from the center of Earth to here will be the radius of the Earth plus Y, right? R will be the radius of the Earth plus Y. And Y, I mean, remember the radius of the Earth is 6.38 times 10 to the 6 meters, so about 6 million meters. So if you're 10 meters high or 100 meters or even 1,000 meters, it's approximately the same. It's still 1,000 meters or a kilometer is much less than 6,000 kilometers. So it's still much less. So it's better than this. It would be like 0.0001 or even better. So we get G will equal to negative capital G capital M little m divided by R, but R here will be the radius of the Earth plus this height Y. I'm going to factor the radius of the Earth, so I get negative capital G capital M over little m, and then here the radius of the Earth times 1 plus Y over the radius of the Earth. I just factored it out. And I'm going to modify this yet one more time, so I get U is equal to negative capital G capital M little m divided by R Earth times 1 over something is that something to the negative 1, negative first power. So 1 plus Y over R Earth to the negative 1 power. So notice, my X here, right, I'm going to use this. It's 1 plus X to the nth power. The 1 is the 1. And then the X will be the Y over R Earth. And then capital little n here will be the negative 1. So this will be approximately equal to negative capital G capital M little m divided by R Earth times what? Well, 1 plus n times x. Well, the n is negative 1. And then the x is whatever is here, Y over RE. And let's expand this a little bit more. Let me just check the timer here. Oh, I have 2 more minutes. So let's expand this. So this times 1 would be negative G capital M over little m over R Earth. And then minus times minus is plus, so I have negative G capital M. The little m, I'm going to write it in front, and then R Earth times Y over R Earth, and then this becomes negative G capital M little m divided by R Earth, and then plus this will be M G M, and then R Earth is R Earth squared times Y. And remember what this is, capital G M times the mass of the Earth divided by r squared. That's g, little g, 9.8. And so this becomes mgy, and this is the potential energy near the surface, at the surface of the Earth, with the reference point being infinity. So this is U at our Earth. Now, if we change our definition to be near the surface of the Earth, we're not going to infinity, so we're just always near Earth, so we can choose this to be the zero, so the potential energy near the surface of the Earth would be the usual mgh or mgy. All right, let me pause this and get to the next section.